Good morning, afternoon, or evening, everyone. My name is Nindhia with the student ID number ending in 080. Today, we're moving from the mechanical world of stress and strain into a dominant that is just as critical, if not more so, for the functionality of a product, which is the physical properties of materials. While a beam needs to be strong, a heat sink needs to dissipate heat, a circuit board needs to insulate electricity, and a chemical tank needs to resist corrosion. Understanding these properties is fundamental to selecting the right materials for the job. To put it simply, mechanical properties answers the question, can it withstand the load? Physical properties answers questions like, will it melt in service? Will it conduct heat away or act as an insulator? Will it expand and jam the mechanism when the temperature changes, or will it rust? A key distinction here is that these properties are largely structure insensitive. This means that while a scratch or a small void can significantly reduce your tensile strength, it has a much smaller effect on properties like melting point or density. These are governed by the fundamental atomic bonds and the crystal structure itself. Density is one of the most intuitive properties, mass per unit volume. But its implications are profound. It's not just about how heavy something feels, it's a key driver in the lightweighting of structures. In aerospace and automotive engineering, the goal is often to maximize strength and stiffness while minimizing the weight. This is where we use the metric strength-to-weight ratio and stiffness-to-weight ratio. A material like aluminum with a density 1/3 that of steel can be a superior choice if it provides sufficient strength for the application, leading to massive fuel savings. Specific gravity is a convenient dimensionless number that allows for a quick comparison against a universal reference, water. Looking at this table or this data, you see the clear groupings. Metals are dense, polymers are light, and ceramics fall in between. This isn't just academic. In casting, a dense molten metal will flow differently than a less dense one. In powder metallurgy, the density of the powder influences how it packs and compacts. And for a consumer product, density directly defines its heft and perceived quality. Think of a premium pen versus a disposable one. The classic example is the substitution of steel with aluminum, composites, or even magnesium in everything from aircraft fuselage to laptop cases. The melting point is a direct window into the atomic structure. A high melting point indicates very strong atomic bonds, ionic or covalent bonds that require a tremendous amount of energy to break. This is why ceramics like tungsten carbide have such a high melting point. For manufacturing, this is a primary process selector. You cannot cast iron with a wooden mold, and you cannot weld plastics with a low temperature solder. The melting point sets the rules for the game for all processes involving liquid metals, casting, welding, and soldering. It also defines the upper surface temperature limit for a component. Get too close to the melting point and the material will rapidly lose strength through creep. The melting point gives us a direct look into the atomic heart of a material. It's the temperature where the thermal energy is so high that it overcomes the forces holding the atoms in their orderly solid form. Think of it this way. Materials with strong covalent or ionic bonds, like the carbon-carbon bonds in diamond, or the aluminum-oxygen bonds in alumina, require a tremendous amount of energy to break. This results in very high melting points. Materials with metallic bonds or polymers with weak van der Waals forces between their long chains have much lower melting points. These aren't just a number in the textbook. In manufacturing, the melting point is a gatekeeper. It tells you if you can cast a metal, what kind of furnace you need, and what temperature you must reach to weld. In surface, it sets an absolute upper limit. If you try to use a steel turbine blade too close to its melting point, it will soften and fail catastrophically due to creep. The melting point defines the thermal operating window for every material. Specific heat is the material's thermal inertia. Think of it as the thermal mass. A material with a high specific heat, like water, can absorb a lot of heat energy without its temperature rising very much. This is why water is used in cooling systems. The formula, heat energy equals to mass times specific heat times temperature change, tells us that the energy required to heat something up is directly proportional to its specific heat. This is a key consideration for energy costs in manufacturing. If you need to heat a large vat of a high specific heat material, it will take a lot more energy and time than a material with a low specific heat. In casting, the specific heat of the molten metal determines how much heat must be removed for it to solidify. A high specific heat means it will solidify more slowly. In heat treatment, it controls the heating and cooling rates. In machining, about 98% of the energy used in cutting is converted to heat. The specific heat of the workpiece and the chip determines how much of that heat is carried away with the chip, which is a primary mechanism for cooling and cutting tool. If the heat isn't carried away, it leads to rapid tool wear. Furthermore, components like brake disc or turbine blades undergo thermal fatigue. Their specific heat influences how much energy is stored in each heating cycle, contributing to stress and potential failure. Thermal conductivity, K, is all about the rate of heat transfer. It's not about how much energy can be stored, but how quickly that energy can be moved. Metals are good conductors because of their electron cloud, which transports energy rapidly. Insulators like plastics and ceramic lack these free electrons and rely on slow atomic vibration. The negative sign in Fourier's law is a simple convention to ensure that heat flux, Q, is a positive number since heat flows from high to low temperature, making the gradient dT per dx negative. Now, this is where the rubber meets the road. You might think high conductivity is good or low conductivity is bad, but in manufacturing, it's never that simple. Thermal conductivity is a double-edged sword, and whether it's an asset or a liability depends entirely on the process you're using. Let's break it down in 3 areas. First, let's talk about machining. In this process, you have a cutting tool trying to shear off a tiny piece of metal, and this generates an immense amount of heat concentrated on the very edge of your tool. If that heat isn't removed, the tool softens, wears out, and fails fast. Scenario A, you're machining aluminum, which is a great conductor. This is a good situation. The heat generated at the cutting tip doesn't just stay there. It does 2 things. It gets carried away by the chip, which acts like a tiny disposable heat sink, and it gets conducted back into the main body of the workpiece. This natural heat dissipation keeps the tool's cutting edge relatively cool, allowing it to last for a long time. Scenario B, you're machining titanium, a poor conductor. This is a challenge. Titanium acts like a thermal barrier. The heat from cutting can escape into the workpiece. It gets trapped right at the tool workpiece interface. This creates a tiny, incredibly hot zone that literally cooks the cutting tool, leading to rapid wear and failure. This is why machining titanium requires special strategies, like high-pressure coolant to force heat out. Now, let's flip to the opposite process, welding. Here, the goal is to create a localized molten puddle to fuse 2 pieces together. Scenario A, you're welding copper. Again, a fantastic conductor. This is difficult. You apply your torch or arc, and the copper immediately acts like a highway, spreading that heat out across the entire part. You're trying to build a bonfire, but the material keeps stealing your firewood. You need a much more powerful, concentrated heat source to overcome this and finally create that molten puddle. Scenario B, you're welding stainless steel, a much poorer conductor. This is easier. The heat from your torch doesn't wander off. It stays put, right where you aim it, allowing a puddle to form quickly and efficiently with less overall energy input. Finally, consider processes like casting and hot working. Here, conductivity controls the clock. A metal with high conductivity, like pure aluminum, will solidify rapidly in a mold because the heat is pulled out quickly. This can lead to a finer grain structure, which is often desirable. A metal with low conductivity, like a stainless steel, will solidify much more slowly as the heat is trapped inside. This requires different mold design and process control to prevent defects like large, weak grains or shrinkage porosity. So the takeaway is, there is no good or bad thermal conductivity. There is only appropriate for the process. As a manufacturing engineer, you don't just accept this property, but you design your process, your tooling, and your parameters around it. This is one of the most critical properties for dimensional stability. All materials expand when heated because the atoms vibrate more and push each other slightly farther apart. The coefficient of thermal expansion quantifies this. It's crucial to remember that this is a material property. Generally, materials with strong, stiff bond, high melting points, and high modules of elasticity has a lower coefficient of thermal expansion, as their atoms are more resistant to being pushed apart. Failure to account for thermal expansion can be catastrophic. If expansion is constrained, it generates immense thermal stress that can bend, crack, or shatter components. In precision engineering, like a watch or microscope, even tiny unaccounted for expansions ruin accuracy. When assembling parts, you must match the values. A steel piston in an aluminum engine block is a classic example. The aluminum expands almost twice as much as the steel, which must be carefully accounted for in the design of piston clearance. Bimetallic strips exploit this difference to act as thermostats. And the ultimate example is INVAR, an iron-nickel alloy with a coefficient of thermal expansion so low it's used in applications where dimensions must not change, like precision instruments and the frame of James Webb Space Telescope, which must remain stable in the extreme cold of space. So far, we focused on the materials respond to mechanical forces and heat. Now we enter a new domain, how they interact with the fundamental forces of electricity, magnetism, and light. This is what enables virtually all modern technology, from the smartphone in your pocket to the power grid that charges it. Let's start with electrical resistivity. Think of this as the material's inherent opposition to the flow of electrical current. It's the inverse of conductivity. Why do materials have such different resistivities? It all comes down to the availability of free or mobile electrons. Conductors, primarily metals like copper or aluminum, have a sea of these free electrons that can move easily when a voltage is applied. They have very low resistivity. Insulators, like ceramics, for example alumina, and most plastics, have their electrons tightly bound to their atoms. They have very high resistivity. They often block current flow. And then there are semiconductors, like silicon and germanium. This is where the magic of modern electronics happen. Their resistivity is in between, but its most important features is that it can be precisely and dramatically controlled, tuned, by adding tiny amounts of impurities, a process called doping. By controlling resistivity, we can create switches, transistors, memory, and processors on a tiny chip. This controlled resistivity is the foundation of the entire digital age. Now, let's shift to magnetic properties. We can categorize materials based on their response to a magnetic field. Diamagnetic materials are weakly repelled by a magnetic field. This is a very subtle effect present in all materials, but it's often overshadowed. Think of water or copper. Paramagnetic materials are weakly attracted to a magnetic field. Aluminium and platinum are examples. The real workhorses are ferromagnetic materials. These are the ones we commonly think of as magnetic. They are strongly attracted to magnets and can themselves become permanent magnets. Some of the classic examples are iron, nickel, and cobalt. But here's the critical engineering distinction within ferromagnetic materials. Soft magnetic materials, these are materials that are easy to magnetize and demagnetize. They don't retain their magnetism well. So why is it useful? Because if you're building a transformer core or an electric motor, you need the magnetic field to switch direction rapidly, 60 times per second or more, with minimal energy loss. Silicon steel is a perfect example of a soft magnetic material. Its magnetism is temporary and responsive. There's also hard magnetic materials. These are the opposite. They are difficult to magnetize, but once magnetized, they retain their magnetism strongly. They are used for permanent magnets. Think of magnets in your headphones, speakers, or the tiny powerful motors in a drone. These are often made from alloys. Their magnetism is permanent and stable. So in summary, electrical resistivity gives us control over electrons to process information, while magnetic properties allows us to convert between electrical energy and mechanical motion or to store information. Now, we'll see how materials manipulate the third key player, which is light. Optical properties determine how a material interacts with light. Transparency is not just for windows. Optical fibers, which are the backbone of the internet, rely on ultra-pure glass that is transparent to light signals over long distances. The reflectivity of a material is key for mirrors, lighting fixtures, and even the aesthetic finish on a product. The choice between transparent, translucent, and opaque materials is a fundamental design decision affecting safety, aesthetic, and function. From the polycarbonate lens of a safety goggles to the opaque housing of a power tool. Moving on, we have 3.8, which is about corrosion resistance. Corrosion is the silent, expensive enemy. It's an electrochemical process, essentially a battery on the surface of your material. It requires 4 elements: an anode, where metal is lost; a cathode, where a reaction like reduction occurs; an electrolyte, a conductive liquid, even a thin film of water; and a metallic path connecting them. The most common form is the oxidation of metals back to their more stable ore-like state. Galvanic corrosion is a particularly aggressive form that occurs when 2 dissimilar metals are in contact in an electrolyte. The less noble metal, the anode, corrodes rapidly. Moving from understanding corrosion to preventing it is a critical design and manufacturing function. The strategies we employ form a multi-layered defense against this electrochemical attack. The first and most fundamental line of defense is material selection. The goal is to choose a material that is inherently stable. The best example are stainless steel and aluminum. These metals don't just resist corrosion, they actively fight it by forming a microscopic, tightly adhered oxide layer, chromium oxide for stainless steel, aluminum oxide for aluminum. This passive layer acts as a protective shield, preventing further environmental attack. When the base metal isn't sufficiently resistant, we apply coatings. The principle is simple. Create a physical barrier. This can be a paint or polymer coating, galvanizing, which is coating steel in layers of zinc. For larger critical infrastructures, we use active protection, which is cathodic protection. This is where we directly use the principle of galvanic sears to our advantages. There are two main methods. The first, sacrificial anodes, where we deliberately attach a block of a more anodic metal, like magnesium or zinc, to the structure we want to protect. This anode sacrifices itself, corroding over time, while the structure remains cathodic and safe. These anodes must be periodically replaced. There is also impressed current for even larger structures. We use an external power source to force electrons onto the structure, making it cathodic. This is like a permanent automated battery system fighting corrosion. Often, the most cost-effective strategy is smart design. This is about eliminating the conditions that allow corrosion to start. Insulate dismissal metals. If you must use steel bolts on an aluminum frame, use a plastic or rubber washer to break the electrical connection. No metallic path, no galvanic cell. Avoid crevices. Design joints to be welded or fully sealed, not overlap where water can be trapped. Crevices create concentrated, aggressive corrosion cells. Promote drainage. Ensure that water cannot pool on a surface. Design with drainage holes. Finally, if possible, we can control the environment itself. Use corrosion inhibitors in closed-loop systems like engine coolants. Control humidity or remove oxygen and salts from water in industrial systems. The key takeaway is that corrosion control is not an afterthought. It must be designed from the very beginning. It's a choice between specifying the right materials, applying a protective system, and design intelligently, or paying the much more higher costs of failure later. Now, if you're looking close at Chapter 3, its core theme is understanding material properties and how they dictate selection for a specific application. There's no better example of this than something we all interact with on a daily basis: coins. A coin is a perfect case study where subjective human factors and rigorous engineering properties collide. Let's break down the 5 criteria for coin selection through the lens of our chapter's principle. First, we start with durability and longevity. Flow. So, we start with the human element. A coin needs to feel valuable and trustworthy. Its weight, density, its ring, acoustic properties, and its cool, smooth feel, thermal conductivity, and hardness all create that perception of quality. But that beautiful, valuable feel is meaningless if the coin doesn't last. This brings us to our second critical criteria, which is durability. A coin that tarnishes or wears smooth in a few years is a failure. So the very property that makes it feel good, like its hard polished surface, must be matched by its core material properties, wear and corrosion resistance. This ensures the design remains legible and the luster lasts for decades, preserving that initial feel throughout its lifespan. Next, we have a material that feels right and lasts well. The next logical question is, can we even make it? This is where manufacturing and security comes in. A material might be perfect on paper, but if it's hard, it will wear out, the coining dies too quickly, making production prohibitively expensive. Furthermore, the material and the stamping process must work together to create features that are difficult to counterfeit. The formability of the metal allows for sharp, intricate designs that are easy for vending machines to verify, but hard for counterfeits to replicate. This seamlessly leads to our next point: machine compatibility. We've just mentioned how the design helps with security, and a key part of that security is interaction with machines. This isn't just about stopping counterfeits, it's about functioning in an automated world. The properties we've already discussed, dimensional stability, hardness, and electrical conductivity, are precisely what vending machines and turnstiles test for. They check for the correct diameter and thickness, which are maintained by the material's wear resistance. They test electrical conductivity and density, which are intrinsic material properties. If a coin fails any of these, it's rejected. So the material must be engineered not just for people, but for the machines that serve them. So we have a material that feels right, lasts long, can be manufactured securely, and works in machines. This leads to the final and often decisive hurdle. Is it practical? All the ideal properties in the world are irrelevant if the raw material is too expensive or too rare. The cost of metals and the minting process must be less than the coin's face value. There also must be stable and sufficient supply of the material to mint billions of coins without disruption. This is why we see coins made from copper, nickel, clads, or steel alloys instead of pure silver or gold today. So, to bring it all together, the humble coin is a masterpiece of balanced engineering. Its selection isn't about finding one perfect property, but about optimizing a portfolio of properties, from the subjective feel to the hard economics of cost and supply. It's a tangible, everyday example of the core principle from Chapter 3. Successful material selection is a multidisciplinary compromise, where science, engineering, human factors, and economics all have to align to create a successful and enduring product. That is all that I have to offer for this video. If I've mistaken anything, I apologize deeply. Thank you so much for listening, and that will be the end for today. Thank you.